Hello and welcome to Diplomatic Derivatives. In today's video, we're going to tackle a very important concept, a very important theorem of cyclic groups, which is going to be, whose conclusion is going to be used in many future concepts. So we'll see what that is. Let G be a cyclic group of order n. Then there exists one and only one subgroup of order D if and only if D divides n. That is D divides n. Okay. So first, what we do is we try to understand each and every part of this theorem so that does not become complicated. So let's continue. What does it mean? That is, we're going to take each and every term from the theorem. A cyclic group like G is generated by A contains all powers of a single element A. This is a basic definition of what a cyclic group is. Let G be a cyclic group of order n. So from this, a cyclic group itself is what? That is a group which is generated by an element, right? And all the rest of the elements are going to be powers of this single element, right? Of order n. So what is the order? Order of a group is n. So therefore a raised to n is equal to e, which is the identity. Again, the definition of the cyclic group. So if you have any confusion for the cyclic group part, make sure you watch the video which explains cyclic groups in detail. This theorem says if you pick any number d that divides n. Now we are going to take any number d. Let's suppose if we have n is equal to n is 6, okay, which is the order of the group. Therefore, there are 6 elements. We take a number d which is equal to 3, let's suppose. So according to the theorem, if you pick any number d that divides n, now does d divide n here? N divided by d is 6 by 3, right, which is equal to 2. Therefore, d divides n. Then what happens? There exists one subgroup of G with order D. So there will be a subgroup of G which will have this order. What order? 3. Okay. Not more than 1, just 1. Just 1 is the most important thing here. There is only one subgroup that will have this order, not more than 1. Okay. So we are now going to prove both of these parts step one by one. First, we make sure that we prove that there's one subgroup of G with this order. In what case? When D divides n. Okay, and then we will prove that it's the only one. Okay, so let's continue. Let G is equal to generated by A and AN is equal to E. So this is what we are saying is according to the theorem, there is a cyclic group of order n. So we will just write it in the notation form. G is generated by A and A raised to n is equal to E. So G is equal to, this is the group according to the cyclic group definition, E and A square, so on till A raised to n. This group has the order n. Okay, this is what is given to us in the theorem. Now what we're going to do is, this is what now we're going to prove. Okay, suppose D divides n. D divides n means what? It means n is divided by D, right? This we are going to take as equal to an integer. We are going to assume that that integer is k. So when you take D on the other side, it becomes n is equal to kt. Now what are we doing here? What are these things? The n is an order of the group, and D is the order of a subgroup, which we are assuming that there is a subgroup. We have to basically prove that there is a subgroup with order D. Okay, so what we do is we divide these two according to the theorem which says that there is a subgroup of order D when D divides n. Okay, so we take the orders and we divide them, okay, and we make them equal to some integer. Therefore, that integer will be also an order, right? So if this is an order and we take it in the form of powers according to A raised to n is equal to E, similarly A raised to D, and here it will be A raised to K. So we have formed an element which is A raised to K. Okay, A raised to n is an element, right? A raised to D will be an element. Similarly, A raised to K will be an element. Okay, so we define a new element which is A raised to K. Now let's look at its power. We look at the powers of A raised to K. When we had A raised to n, which is equal to E, we had the generator here is A, right? From A we got A square, so on till A raised to n minus 1, right? The generator was A. Now in place of A, the generator is what? AK. So it will be AK raised to 1, AK raised to 2, and so on, right? So it will be ak to a2k till ak raised to d. Why we are taking d? Because it's a subgroup. Okay, it's not a group, it's a subgroup, which is why, because that's why is that happening, because we have kd over here. Okay, so it's going to be a raised to k raised to d. Now you will multiply k into d will become kd, a raised to kd. Now kd we know is equal to n, according to n is equal to kd, so it will be a raised to n, which is equal to the identity according to the first statement, right? So when we get this, the subgroup is generated by ak, which is h. Now we take the name of the subgroup as h, right? Which is now generated by ak, all right? Which is equal to what? E comma ak, which is the first element, the generator, same like this. Okay, a2k. When the generator was a, you got a square, right? Here the generator is ak, so it will be a2k. Okay, so on till when it was an, the last element was n minus 1, right? Now it is about the subgroup, which is about d, right? So the last element will be d minus 1 raised to k. Why k? Because the generator is ak, it's not just a, right? If it was a L, let's suppose, so it will be a n minus 1 raised to L, right? So in the similar manner, it's a k, so we get ad minus 1 raised to k. This subgroup has exactly d elements. Like this group has exactly n elements, this one has d elements and has the order d. So we have constructed a subgroup of order d. Therefore, this is how we got the subgroup, right? So now the first part is proven, that there is a subgroup when d divides n. All right, now we move to the second part of the theorem, which says that it's the only one. There is only one of us of this order. There is no other subgroup of a similar order. So how do we do that? Suppose there is another subgroup k. Now we have one group will have many other subgroups, right? So one we got was h with the order d. Now we take another subgroup and we say that the order is k, right? So sorry, the subgroup is k and it also has a similar order as h, which is d. Now this time this k is generated by a l. H was generated by a k. This k is generated by a l, but the orders are same. Okay, what we do is we show that this generator al is also equal to h. This means what? That both these subgroups are the same. Okay, this al when generates k, al also generates h. If this is the case, then both of them must be same. This is what we are going to prove. Since k is generated by al, has order d, that means what? That since the order is d, we can write al raised to d, because when the order was a in the previous slide, as we saw, for a group the order was a, so it was a raised to n, right? Since n was the order. Here al is the generator, so al will be raised to the order which is d. So ld, it will be ald, which will be equal to e, right? Why is it equal to e? Because we saw that in the previous slide it was an was equal to e, right? So similarly ald will be equal to e. So n divides ld according to similar thing that we did in the previous slide. When d divides n, in a similar way here n divides ld, since what? An is equal to e, okay, and am is equal to e, which means n divides m. When we saw that in the previous slide, what did we have? We have a raised to n, right? This is what we had, right? Now if there is another thing, a raised to m, which is also equal to e, what does this mean? This means that n divides m, okay? That is m divided by n, when both of them are equal to e. Okay, this is already proven. This is also proven according to one of the theorem that we did earlier. You can check the previous theorem that I explained in one of the previous videos. There also we proved the similar thing. Okay, so this means that m is divided by n. Similarly, it will, since ALD is equal to E and AN is equal to E, therefore n divides LD. Okay, that is LD divided by n. But we already know that n is equal to KD. So When we write this n divides LD, what is it? It can be written as LD divided by n, right? We assume that it is equal to some integer r. So when n comes on this side, it will become LD is equal to Rn, right? In place of n, we can write KD. So it will be LD is equal to RKD. D and D gets cancelled, so we get L is equal to RK. Now this is what we got till now. L is equal to RK. So we just write it here. This is what we got. L is equal to RK. Okay. Now, just there's a mistake here. So these are all power. So this is power L. This is again in power RK. Here also this is K in power, and R is also in power, and here K is also in power. Okay, so that's just by mistake. Now, A raised to L. Now, from this statement, we are going to put it all in powers, because we know that as we did in the first case when we took everything in powers. So we can take, since L is also in order and K is also in order, so it will become A raised to L, which is equal to A raised to RK. Now this can be written as A raised to K in the bracket and then raised to R, right? So we know that this A raised to K is already generating what? It's generating H, right? So therefore, when again here it's a mistake. Since A raised to K is generating H, and that thing is equal to what? That thing is equal to A raised to L. Okay. Therefore, AL is also element of H. When AK is generating H, it means AK is element of H, right? Similarly, when AK is AK raised to R, okay, so there is AK, right? So AK is also equal to AL. This means that AL is also in H, which implies K, which is generated by AL, is a subset of H. So since AL is inside H and AL is generating K, so K will be inside H, okay? But both K and H have order D. Both of them have a similar order, right? They're equal to each other. So if one is inside the other, they must be equal. If K is inside H, then they must also be equal. Therefore, H is equal to K, okay? So this is proving that there is only one subgroup of having the order D, that is having a single order, similar order. If H has order D, then if we are taking another subgroup which is also having the order D, then it proves that these two subgroups are same. They are not different, because only one subgroup must exist that must have the order D. And all of this is happening when D divides N. Okay, so this is the proof of the theorem. So it's kind of all over the place, kind of complicated, but just make sure that you understand the basic concepts, how to do it. Because first you're basically starting from a single statement that it's a cyclic group, and from that is what you're building the entire proof. Okay. So what is the most important thing that you need to consider get from this theorem? What are you getting from this theorem is that when D divides N, so when we have any group that has an order N, and there is an integer which is D which divides N. So let's suppose that when we take a similar example, when N is equal to 6, let's suppose, and D is equal to, let's suppose, 3. So we know that here D divides N, right? We get 2 from the division, right? There exists a subgroup of order D such that A raised to N by D. So that subgroup will be generated by an element which is N by D. Okay, this is what we are getting from this proof, that when D divides N, there exists a subgroup of order D, and also that it's the only one. So any other subgroup of order D must be equal to this subgroup. There is no other subgroup which can have a similar order. Okay, there is only one subgroup of having this order. Understood? So if that was clear, I hope it was made clear as much as I could. I tried. We are going to take in the next video an example of a group, and we're going to generate cyclic subgroups for that group. So through that, what that will be basically, the group will be Z18. Okay, and for Z18 we are going to generate cyclic subgroups of this group. Okay, and that is going to be done by using this idea of D divides N. Alright, the idea of this theorem will be utilized in order to find the cyclic group. These kind of questions come in exams. You can also check one of the past papers of CSS where this question, or I think it was Z12 or maybe Z18, so I don't exactly remember, but this question came that you have to generate cyclic subgroups of the given group. Right, so this is a theorem that is utilized in order to solve that question. This will be seeing in the next video. So make sure you like, share and subscribe to my channel, and do ask any questions if you have related to this video or any other video that you have seen previously. And after this example, we'll be seeing another concept which is also very important, that's cosets and its theorems. And this concept of the cosets is going to allow us to understand the most important theorem of the group theory, which is the Lagrange's theorem. So make sure you continue watching my videos and support my channel. And that's it for today. See you in the next one. Bye bye.